Okay, so now for the second session, we are kind of like taking a step back and talk about a few more general prerequisites, such that you can really follow our presentations, our future presentations, and our exercises. There's mostly two topics I want to cover. One is like the kind of meshes we are looking at as they arise in finite volume methods. And afterwards, it's going to be a few general prerequisites in vector analysis. So assuming you're like a model developer or you were exposed to a lot of numerics in your career, then you can safely zone out for about 15 minutes. But if not, I hope this will be at least somewhat useful to you. So as you might know, well, as you do know, there are quite a few different numerical models in operation all over the world. And one of the most, or probably arguably the most important difference they have between each other is the numerical methods they employ. So just to name a few which are currently important, then the first of all, and maybe most basic of all, are the finite differences, which are historically important, but there are still at least one model still in operation which uses finite differences as the most central numerical paradigm. And currently, probably more widespread, there are the finite volumes. There are also spectral methods, and I believe we have also seen in the Cyclone presentation some stuff about more modern methods like the discontinuous Galerkin methods. And it doesn't matter that much right now how each of these methods differ or what exactly they do. However, what I would like you to understand right now is that depending on which numerical method you support, you can then, as a consequence, support different meshes. Like finite differences are most appropriate on Cartesian meshes, whereas, for example, if you choose finite volumes, you can, or as a consequence, maybe have to support more general meshes, which can be unstructured, and even support like different geometrical primitives in the same mesh. Like you could reasonably have squares and triangles intermixed in a finite volume mesh. Okay, but still, no matter whether you are on a finite volume mesh or you are on a Cartesian mesh for finite differences, one thing your meshes will have in common is that they are neatly arranged in columns. So as you can hopefully see on this slide where we have a numerical weather prediction like mesh, you can see that you have these coordinates or these squares or panels, and they are neatly arranged in columns, which we have re-illustrated here. So for each area above your surface, let's say, you have a column which is not uniformly spaced usually, but you have a well-defined lower and upper neighbor. And this is a consequence because we are assuming that the Earth is a height field, like that the terrain would never overhang or stuff like this, which is a reasonable assumption to make, I would say. However, this column-like property is not at all a general property in CFD. Like in CFD, you would usually have meshes which are way more freely arranged, let's say. So for example, on the right-hand side, we would have a mesh as we could encounter it when we try to simulate the airflow past an airfoil. And you can see that in this particular mesh, it has the same property right around the airfoil, at least at the top and at the bottom. But when you further go away, like the designers of this mesh decided to apply a coarsening, and then you quickly lose that property that you have this well-defined upper and lower neighbor. And you would need to give up a few conceptual and performance optimizations which are possible in NWP, but not in more general CFD. The other thing which you have already been able to observe is that these meshes, they follow the ground or the terrain closely. So especially in the lower layers, you have the individual panels still following the terrain closely. And as you go further up, they still follow the terrain, yeah, almost as close. But if you go further up and further up, the terrain following property of the coordinate is further smoothed out until it virtually becomes flat. Okay, so this answers how these columns behave, but we didn't discuss yet how you come even up with these columns, like how you subdivide the space upon the Earth and on which to build up the columns. And again, there is various different ways on how to approach that, all with different strengths and weaknesses. So the most natural or the most immediately clear approach could be that you try to follow the latitude and longitudinal grid about the Earth to come up with your numerical mesh. And this might be a solid plan, especially if you are intending to use finite differences, because this is at least very close to a Cartesian mesh, right? And however, an immediate problem you already have if you chose this way to subdivide the Earth is at the poles, because at the poles you would get a singularity, and your mesh cells would get infinitesimally small. So you would need to support an infinitely small time step, which is of course not possible. So typically, if you have global simulations in mind, this might not be the most appropriate mesh to use. And another approach I just want to mention briefly is like that you could make kind of like a cubed sphere. You say that in the first subdivision level, so to speak, your Earth is a cube, and then you start to subdivide that, which, for example, is in use in the open source FV cubed or FV3 model. Or yet another way could be that you do this icosahedral subdivision, which I want to talk about a little bit more closely now. Sorry, 1 second. Because the Icon model, which is the model we are most interested in over at MetaSwiss, because this is also the model which drives the current development of Dusk and Dawn, uses this icosahedral subdivision. So how does this work? So here we assume that the Earth is an icosahedron in the first step, which is nothing but a 20-sided dice. So we kind of wrap this 20-sided dice around the Earth, which gives us 20 neat big triangles. And then we start to subdivide that triangles in a first level and then in more and more levels. And then in the end, we would also optimize this mesh a little bit with a mass spring system to get nice uniform triangles. So what is special about this, or what is tricky about this? So, well, we are in a close to structured situation. We almost have like this triangular structure on the primary mesh with a hexagonal neighborhood, like six neighborhoods everywhere, except at the boundaries where we have pentagons. So like at the original corners over here, you can see that there is a 5-fold neighborhood, whereas in the subdivisions, you have 6 neighbors. So you get this kind of almost structured domain. However, for all of the exercises and for most considerations throughout our talks, we are only going to talk about small slabs or small pieces of the mesh, which do not happen to contain a corner. So here we have this triangular structure with always these hexagons in the dual mesh. And one thing which I believe is almost immediately clear is that this mesh has different entities. We have the nodes, we have the edges, and we have cells. And well, what is maybe not immediately clear is that different prognostic variables are going to be located on different entities. So you are not going to have a co-location of all variables or only nodes or only cells. So for example, in Icon, the designers decided that they're going to split the variables as follows, that you're going to have, for example, temperature and pressure on the cell centroids, you're going to have the velocities, or the normal components of the velocities rather, on the centers of the edges, and you're going to have the vorticities on the corners. And this has severe numerical consequences how you're going to do that split. But again, this is not so important right now. What is important to know is right now is simply that not all variables are going to be on the same entity. Okay, then on to the other part of this more general introduction, where it's just about 3 quantities from vector analysis, which you will need to understand to really thoroughly understand our exercises. So it's just going to be 3 quantities and 1 theorem, which is all you're going to need. And for these vector analytical quantities, there is always a formulation which is general, which is true on Cartesian meshes, which is true, on Cartesian coordinates, which is true on spherical coordinates, on curvilinear coordinates, pretty much whatever you choose. And on the right-hand side, you have the more familiar formulation on the Cartesian mesh. Now, it turns out for me, if I want to develop an intuitive understanding of the quantity in question, for me, the more general formulation is the one which is more intuitively clear. So yeah, for me, usually it makes more sense to try to explain in words what's happening on the left-hand side than to make sense out of the differentials which are listed on the right-hand side. So for example, to understand the gradient, what one can do is, like, we have this limit of a volume, V or delta V, which goes to 0, and we have a surface around this volume. And if I try to understand this quantity, what I usually do, I try to understand what's happening on this volume when I realize this is mathematically questionable, but still, I try to understand what's happening shortly before this volume goes to 0. So here we would have a volume with a surface, and we have a scalar field f. And what we are doing due to this surface integral, we are walking around that volume, and at each point we are scaling the outside unit normal by the scalar field f. So what would happen if that scalar field f is bigger on the right-hand side of this small volume than on the left-hand side? Well, then the unit normals on the right-hand side would be weighted more than the volume than the unit normals on the left-hand side, and you end up with a vector which points to the right side. So if you do this, you walk around your normals and you collect this in this way I just described, then you would end up with a resulting vector which points to the right, or more formally, which points into the steepest ascent of the scalar field f, which is nothing but the gradient. For the divergence, which operates on a vector and it gives a scalar, we can make a very similar argument. This time we are again on our volume, and we are again doing our walk around that volume. But this time we are seeing a vector field and a unit normal, and we're taking the dot product. So if we are seeing a vector field which is very collinear with the outside normals, we would get a large value. So which means that we would get a lot of quantity flowing outside of the current volume, which is an intuitive argument for the reason that the divergence is a measure for the intensity of the point source inside that infinitesimally small volume. And finally, for the last quantity, for the curl, we again have a vector field, and we expect a vector in return. But at this time, we are not taking the dot product to the unit outside normal. We are taking the cross product. And if we encounter a lot of vectors which are perpendicular to our outside normal, we will get a vector, a result vector, which reflects the strength of the vorticity, like how strongly the current vector field flows or circulates around this infinitesimally small volume. Okay, here again, just having the same thing as an overview in a table. We have the gradient, which operates on a scalar field and gives back a vector, which points into the steepest ascent. We have the divergence, which takes as an argument a vector field, returns a scalar, which is a measure for the source density. And then we also have the curl, which takes as an argument a vector and returns another vector, which reflects the vortex strength at each point in space. Finally, one theorem which we need as a prerequisite, which is the widespread green Gauss theorem, also known as just Gauss theorem or divergence theorem. And this relates the divergence over a volume to the flow over the boundary of that volume. So basically, all that means is that a quantity, so we remember that the divergence is a measure for the source strength. And if we integrate the source strength in a volume V over the whole volume, then basically we need all of this stuff which is produced inside volume V needs to flow over the boundary of the volume, which we can then add up with this surface integral. So all this means is all of which is produced in a volume B has to flow over the boundary of the volume B. Okay, and that's already pretty much it. These are all the prerequisites which you need to understand, especially what is going to be happening in the exercises.
Thank you very much, Matthias. You will all see all this in action in the following exercises, probably more starting from tomorrow, but we will use all these theorems and definitions. Now we should ask questions to clarify. Is there anything to clarify about this concept? Remember, you should write in the Google Doc. Questions from Matthias? Okay.
Looks like you're good here, I guess. Yep, perfect.
Yeah. Still, if there is a question, you can write it there, and then Matthias can have a look at it
later or even in the Slack. Yeah. If not, thanks for your attention.